Now we're going to move one step closer to blood plasma by introducing a weak acid. We could just as easily introduce a weak base. However, the analysis is very similar, and weak bases are not commonly encountered in plasma at concentrations that meaningfully affect the acid-base status. Clearly, a weak acid is a substance which only partially dissociates. The key example in human physiology is in fact plasma proteins. The amino acids dissociate and act as weak acids. In theory, we should have a separate dissociation equation for each amino acid. However, it's a reasonable approximation to follow Stewart's approach and lump all these dissociation equations for each amino acid together as a single dissociation reaction with a representative dissociation constant, which we will call K subscript A. We will also use grams per deciliter as the concentration units for proteins, with internal conversion in our computer program to the appropriate millimoles or moles per liter as required for calculations. This is simply to ensure that we use units which are clinically familiar. Before we move on, I should draw your attention to a few points about weak acids. First, it is clearly not only plasma proteins that behave as weak acids. There are also other contributions, such as the small contribution from phosphates, and even non-physiological effects like some drugs. However, even the proteins are a little more complex than one may think. The idea was introduced that it is not the entire plasma protein level that behaves as a weak acid, but rather just the albumin concentration. This does not prevent us using total plasma proteins in our Stewart calculations, because the effective dissociation coefficient is experimental, and thus the split between albumin and other plasma proteins is already built into it. However, doing it this way assumes that the ratio of albumin to total proteins is within a very tight range. To the extent that this may not be true, such as in hypoalbuminemia, this would need to be taken into account, and it may then make sense to use only albumin with an appropriate dissociation coefficient. However, as the purpose of this course is understanding rather than precision, we will revert to treating total proteins as the only weak acid. Our weak acid, proteins for example, has the following dissociation reaction. HA is in dynamic equilibrium with H plus and A minus, where HA is actually our acid, with the H representing the hydrogen ion component which will dissociate. This could be an acidic drug, or it could be our plasma protein. We now have four equations, in other words, four conditions which must be satisfied simultaneously. And these are, as always, H plus times OH minus is equal to K prime W. But now we have two new equations relating to the weak acid. They are H plus times A minus is equal to Ka times HA. And here Ka is our dissociation constant for the weak acid. And then we have A minus plus HA concentration is equal to the A total concentration, or A tot as we've called it here, which is simply a statement of conservation of mass, which indicates that the total amount of A, whether it is in the form of A minus or HA, must be constant and is called A tot. Thus, A total or A tot is the total amount of weak acid, such as plasma protein. And finally, we have the fourth equation, which is electrical neutrality. And this has been changed because we now have the weak anion A minus. So it now reads SiD plus hydrogen ion concentration minus hydroxyl ion concentration minus A minus concentration is equal to 0. Note that SiD is just our net concentration of strong ions and is designated SiD in square brackets. You may want to think about what the effect is of adding a weak base. Now let's look at the effect of adding this weak acid. When we solve these four simultaneous equations, we get the following curves for H plus and OH minus, which are drawn as a function of SiD. Note that we are using values for Ka and K prime W that are suitable for 37 degrees Celsius or body temperature. The curves, as you will see, are steeper than in the purely strong ion case in the previous video. And there is a shift of the neutrality point, in other words, where the hydrogen ion and hydroxyl ion concentrations are equal to each other, to a positive SiD value instead of 0. In other words, the H plus and the OH minus curves cross at a value that's positive instead of simply 0 as happened in the strong iron case alone. The exact SID value to give neutrality will depend on the concentration of weak acid.